Dzień dobry, good morning. So yes, thank you for being here at 9 a.m. We all know that for game developers this is really early, so I'll make it worth your while. So yes, this is going to be a technical talk about building scalable game servers. And by scalable, what we mean is game servers that grow with you. As you start out with a small game, maybe dozens, hundreds of players, and grow into, hopefully, as you grow into thousands of players, maybe even millions of players. So that's the theme of this talk. One slide about me real quick. My name's Robert Zubek. So a fun fact, I'm actually Polish. I was born in Poland, but my parents emigrated. So I've lived in the United States most of my life. And I graduated with a PhD in computer science in 2005, and I've been working in the industry for the last 10 years. Started Electronic Arts, Lord of the Rings franchise, Sims franchise. Then went to a company called Three Rings, which was later acquired by Sega. We were working on a casual MMO, if you can imagine such a thing. Then I went to work at Zynga, where we made Cityville and Farmville 2. These are two of the largest social games out there. And then a couple of years ago, founded SomaSim, and we make single-player strategy games. So a very different kind of a thing. The reason why I'm mentioning this is that out of the last 10 years in the industry, I've spent 6 of those working on multiplayer games. So I've had the pleasure of working with some really talented people and learning a lot from them. And I'm hoping to relay some of this information to you today. So this talk, as I mentioned, is going to be about building scalable game servers, specifically looking at async servers for things like mobile games, social games, etc. We're going to be talking about scalability. And the theme of the talk is going to be really reusing web solutions for this, because they tend to be really well matched for async games. So that's that in short. We're going to start with a quick intro section. So we'll talk about some definitions, what are the different kinds of scalability, and what are sync servers versus async servers, that kind of stuff. And then we're going to dive right into technological solutions for this. So what do we do about databases to scale them? What do we do about caching in front of those databases? What do we do about servers? And that kind of stuff. So let's jump right into it. The problem with scaling is that everybody wants to start small, right? We start with servers that are fit for our initial player base. Initially, we might have 100 players, 1,000 players, whatever. But we want the ability to scale to many more players as we grow, and also shrink if we don't have those players. Unless you're EA and unless you can predict that you're going to get 1 million players at launch, it doesn't make sense to be provisioning all those servers early on a gamble if you don't know that you're going to need them. So the idea is to have a setup that lets us grow the server base with the game. So the two kinds of growth are basically, do we make a bigger server or do we get more servers? So getting a bigger server is the sort of easier solution, right? Because if we start with a game that's running on just one server, or a tightly integrated cluster of machines, then just getting a bigger machine is the easy solution. It doesn't require changes to code, maybe some changes to configuration, that kind of stuff, but it's very easy. And the downside is kind of obvious, right? If your machine starts getting hot and you replace it with a bigger machine, what are you gonna do when that machine starts getting hot too? You're kind of just postponing the inevitable. You will end up, assuming your game keeps growing, you will end up reaching a ceiling of performance for the machine. However, it is a very good first step, and that's a great solution. But ideally, we would want to switch to scaling out. By scaling out, we mean replacing one server or one little cluster with just a whole lot of different commodity machines that we can split the work across, so that if you have more players, you just add more machines. I mean, that's the goal. The reality of it is that it does require different kinds of engineering, right? Because if you used to have all the players connected to one machine, and now they're all connecting to different machines, what if they need to chat with each other? Do we route messages across them, or what? Like, how do we set this up? That's kind of the challenge. But but the goal is clear, right? If we have this kind of a scale-out setup, if those servers start getting hot, then we just add more servers, and it sort of magically works, right? Wouldn't that be nice? So let's talk about two kinds of online games. Synchronous games, where players play at the same time with each other, and then asynchronous games where players log in and log out and take turns. So asynchronous games are going to be the focus of this talk. Synchronous games, MMOs are a perfect example of those. Players are playing at the same time synchronously. They are very difficult to scale. And if you're interested in MMOs, I would recommend the makers of EVE Online have a great technical blog, and they have a lot of great GDC talks online. I would highly recommend looking at those. It's not going to be the focus of this talk. I'm going to focus on asynchronous games because that's where my experience is. And that's games like your mobile, tablet, social games, some PC games where you take turns, right? One player logs in, sends their armies over in Clash of Clans, or puts together a ward in Words of Friends or whatever, submits the action to the server. Their friend logs in next morning, sees the game has changed, makes their move, logs out. I log back in the next day. I see my friend made him, and so on. Sort of like taking turns and sort of communication with the server in an asynchronous basis, with each other in an asynchronous basis. So what people noticed early on when developing these kinds of games is that the give and take nature, the request response, the I go to the server, get data, then I make my move, and then I log out, that looks a lot like the web, right? That looks like HTTP request response kind of a setup. I request data, I get data, I send an update, I get an OK. So what people, the kind of a solution that people sort of agreed on early on is that these kinds of async games we could potentially implement using web technologies. One, because it's a good match for this async kind of gameplay. Two, because that gives us three distinct advantages. One, the web community, the web developer community, has already developed a lot of know-how about how to scale web servers. So we can reuse their learnings, and they're very open about sharing what they've learned because there are a lot of very large web properties out there, and they share their information. Two, there's a lot of free software out there, which is great, right? Free is always better than not free. And three, it's easy to hire people with experience if you need them. If you need help, you can either get help for free on forums, or you can hire contractors on a part-time basis just to get you through the rough spots. So that's kind of nice. So that's what we're going to talk about, async servers. And if we look at your typical web game backend in this kind of a setup, this ends up looking very much like a standard three-tier web app, right? So we have the presentation layer, which is your game client, your tablet, phone, PC, whatever. Then you have your business logic, in which case this is going to be our game servers, this written as HTTP servlets or servers or what have you. And then they do all the gameplay processing. And then you have your data layer, which is the data has to come from somewhere, right? So your database and whatever else you use. But there are a couple differences. With a web page, you go to google.com or whatever, the web page really doesn't care which server it's talking to. And chances are, if you keep hitting links or whatever on google.com, you're going to be talking to different web servers, and that's fine, because that's how they achieve scalability, right? They have a setup such that no matter which server you talk to, they're all equivalent. It doesn't matter. And that's the key to scalability. We can then just add more servers, and it works. With games, it's a little more different, because if I make my move in a game like that, and I send it to a server, that's fine. But then I make a second move, and that second move really depends on the knowledge and the change in the game state from the first move, right? Because in order to validate my second move, the server has to know what moves did I make before. And if I hit a different server, that server has no idea, right? Because I previously talked to a different one. And then if I send a third move, then that might go to a different server. So that's the difficulty, right? How do we, given this sort of order of operation sensitivity, how do we set this up? And the answer is, unfortunately, well, they all have to share some kind of state together. which means the database has to do all the heavy lifting of actually being kind of like the shared memory between all of these servers that are scaled out. So that's what we end up doing. We end up treating the database as the global game state storage, and that is kind of tricky. So a couple more distinctions there, comparing web pages to games. Mainly that games are really stateful. There's a lot of information that the client needs that they're going to download and then upload back to the server, changes, whatever moves I make, etc. These game states tend to be big, and games have a very high write-to-read ratio in databases. So in a web property, you would typically just read stuff. In a game, you're going to read data from the servers, and then you're going to write it, write an update back. There's a lot of writes going in, which puts strain on the database. And as we mentioned before, the order of updates matters, right? So we're going to start on the technical part now, sort of from the back. We're going to start with the databases because they're the most sensitive part. They're the first ones to fall over when you start growing. And then we're going to go through caching and actually talk about the web servers later on. And just as an aside, this is a very quickly evolving field. Even as recently as 5 years ago, people had to run their own servers, administer everything themselves, install everything, all the pieces, and set them together. These days, actually, things have changed. There are managed solutions that companies like Google and Microsoft will host for you, and they will manage scaling and things like that. We will talk about those towards the end of the talk. And right now, let's switch over to talking about the details. So, as I mentioned, let's start from the databases because they're kind of the most sensitive part. If you start out with a small game and it starts growing, you start getting more and more players, what's going to happen? Your database is going to fall over first because it has a lot of work to do. So, first of all, how do we know when? And I mean, on a single database, you can go for a very long time. You can go up to, who knows, thousands of users maybe, concurrently maybe even, depending on your game and your usage patterns. But at some point, hopefully, you've grown enough that this is going to become a problem. I mean, that's a nice problem to have, right? How do we know when this is going to happen? Because we need to start worrying about this before it happens. And the way to do this is sort of a three-step kind of a thing. First, we benchmark real player impact on the database. So a player logs in, we log all of their queries to a file, and we build up a profile of what's a stereotypical player like, how many inserts, how many selects, how many updates, that kind of stuff per player. And then once we know that, we run a synthetic load test, basically a dummy client that replicates this kind of activity with fake data. But we add more and more of these concurrent players just to see how many concurrent players we can fit. 100 at the same time, 1,000, maybe 10,000. At some point, as you keep ramping up those concurrent players, the database is going to start failing. And it's going to be very noticeable, right? Because the database is going to be happy, 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 and then start falling. So that's your breaking point. So then you basically graph this in a standard way. Your measured queries per second as a function of number of players is going to be hopefully linear, right? Then we have the max queries per second from our synthetic benchmark, and that's how we know, okay, this is the max number of users I can support on this database. And this tells you basically how much time you have before things start going south. So now that we know when to do stuff, what do we do about this? So one of the things that people do in the web world very often is set up read-only slaves, which is a great solution for web properties, because in a web property, most of the stuff is reading. In a game, as we mentioned, you're going to have a very high write ratio, so this doesn't help nearly as much. It's sort of postponing the inevitable, right? Because your master database is going to continue being the bottleneck. So another solution that happens is a multi-master setup, and this is like your typical database cluster maybe. You can connect to any of the masters, send in updates, and those master databases kind of figure out between each other, like what's the real truth. It doesn't get used maybe as often as it could because one, there's a lot of traffic, network traffic between those databases because they have to come to consensus. Two, if you have network delays or problems and you send two different conflicting updates to two of those servers, they're going to have to figure out what the real truth is. And that kind of gets, tricky. So what people end up doing is something really simple and really dumb, but it works, which is so-called sharding, which is shared nothing partitions. If we have data in multiple separate databases that know nothing about each other, then it becomes really simple. There's no traffic between those databases. It's kind of nice. The complexity of this is that all of the logic for where do we put data, where do we read it from, now has to go up to the app layer. Now it has to, your game has to know a lot more about your data layout than it would otherwise. But it kind of works, right? So there are two typical ways of doing that. You have your vertical partitioning, which basically works like this. If your database starts getting hot, you take the table that has the most activity on it and you put it on a different server. And maybe put some other tables on other servers. Basically, you split it up like that, which is nice. It's a good stopgap because it will relieve pressure immediately. However, again, you're postponing the inevitable because at some point, you're going to end up with a server that has one table on it and you can't divide it up anymore. So what people typically do actually is horizontal partition, which is like striping in RAID, right? So let's say we have 4 servers. We just assign rows to them on a round-robin basis. Row 0, row 1, row 2, row 3, 4, 5, 6, 7, and so on. And then if those servers start getting hot, we add 4 more servers, and we change the logic, and we do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So it's easy to just add more servers and add more databases if your databases start getting hot. And that's called basically sharding. Now, there are problems with that. As much as it's a desirable thing, with shared nothing partitions, it becomes really hard to do joins, which is kind of like, well, what good is a database if I can't join across tables? And it's kind of a high price to pay, unfortunately. And since those databases are on different servers, remember they're shared nothing, so they don't talk to each other. So it's hard to do. Again, with integrity checks. Let's say you have a stored procedure that has to check, before you insert an item into a player's table, a player's inventory, we check whether it's not in somebody else's player inventory, something like that. Now, because those inventories are split across multiple servers, that becomes difficult. What this means is, one, again, we put all this logic in the game, up in the app layer, which kind of sucks, but it's usually okay. Two, we start treating the database as just a simple key value store. So if we can switch all of our data to use this kind of API, right, where you have a key, whether it's a player ID or whatever, and we put data into database under that key, and it's just a blob of data, and then we get it using that key, and we don't do anything fancy, we don't do joins in the database, then the scaling works really nicely. And that's how a lot of these scalable managed databases work too. You have to specify your primary key on which data is going to get sharded, and then the servers sort of do their thing. And as we mentioned before, it means pushing a lot of this complexity up to the app layer. So that's good. This kind of sharding helps a lot because now we have a scalable solution to database falling over. But wouldn't it be nice if we didn't have to use the database if we don't have to, right? Because if the database is the sensitive part, can we relieve it from having to do work? So, looking at your game usage, we have 2 players. They take their turns, they make their moves, and it talks to the game servers, and those game servers talk to the database. And the database, remember, has to try to keep the data consistent and safe. So it's going to do a lot of f-syncs to the hard drive, right? Every time somebody makes a move, sync to the hard drive, update the journal, that kind of stuff. That puts a lot of strain on the database. What if we did this? What if we put a cache in front of the database such that the players make their moves, do their things, and we only update the cache, and the cache only stays in memory, and then sometimes, every now and then, maybe after 5 minutes or after 10 moves or whatever, we write it to the database. That's kind of cool, right? Because now we get one database right instead of 10 or whatever. That kind of network attached caching, whether it's memcache or some other solution, or maybe something built in, is very useful. It does come with one downside, which is that if you have a power outage and your network attached cache server goes down, then you've lost all the data. So it's useful in some cases, but not in others. So for example, if you have players making your moves, it's probably okay to lose the last move they made because they're going to log back in and they will say, oh, the server must not have registered my move. I'm going to make my move again. And maybe they will think it's a chance to get another chance at making a better move or something like that. So that's possibly okay. But the one part where it's not okay is when you're actually charging real money for something. When you've sold the player an in-app purchase, you have to write that to the database. It's not acceptable to just lose it when the power goes out. So sort of like, it's one of those contextual, think when it's appropriate kind of a situation. So in the sort of battle days, you had to do this sort of database and caching yourself, set up a database server, set up caching, make them work together, set up alerts, making sure that the connections don't go down and so on. Full control. I wouldn't recommend it. It's kind of a pain in the ass. There are more modern solutions. For example, self-hosted KV databases, which tend to include both. So there's an in-memory component, which is where most of the activity happens, and then they write to disk on a regular basis in sort of a right behind cache, approach. So that's useful. And then there's of course fully hosted databases, such as those provided by Google Cloud Services or Microsoft Azure and so on, which will do that for you. So they will host the database and they will add more servers automatically. And that's really useful. We'll touch on that in a few slides. So let's stop talking about databases and let's talk about servers for a change. So as we mentioned, your game logic, your business logic lives in this sort of middle layer where game servers host your code in form of, if it's Java, it might be applets or your own web servers or whatever. The key to scalability on this layer is that we want to make it possible so that your game clients can talk to any servers and we can just add more servers and it just works. And the way we do that is by making the servers stateless. So they don't care who you talk to, they don't remember anything. So what that looks like is, let's imagine your typical simplified gameplay session, right? So a player starts up the app and maybe they have to first download some assets, your message of the day, whatever, that kind of stuff. And then they start talking to one of the game servers. They might not even know which one. They shouldn't care. And they ask to get the latest game state. So the server goes to the database, authenticates the user, goes to the database, asks the database, give me the game state, sends it back to the player. The player makes some moves and then sends their actions to the web server again. Now for us, for this to be scalable, it shouldn't matter which server it goes to. So the server shouldn't remember anything, which means the server has to go back to the database, fetch the data again, and now process the player's actions, figure out whether it's a valid move. And if it is a valid move, send the update back to the database, and then finally send information back to the player saying, all right, that move was good, you're good. And then the player does the same thing over and over again, right? They go make another move. Which means there's a lot of back and forth between the servers and the database, fetching the data, saving it back, fetching it, saving it back. That's going to be probably your main problem, your main performance bottleneck. Because of that, because your performance is going to be much more limited by all the serialization and deserialization, it's probably best to use a high-performance programming language for the web server. Everybody has their favorites. Maybe it's Java, maybe it's C# or something, because your quality of serialization libraries and the speed of serialization is going to matter a lot. Other than that, sort of going beyond that, your implementation of game servers is kind of up to you, as long as they're stateless. Because if they're stateless, then load balancing and scaling them becomes easy. There are very well-known solutions for this. You basically take all your servers, put a reverse proxy load balancer in front of them. It could be HA proxy, it could be Nginx. There's a bunch of different ones. And it will sort of, shuttle traffic back and forth. If your load balancers start getting hot, then you maybe put in a DNS load balancer in front of them. It's one of those things where once you look up, if you Google HA proxy or some other load balancer documentation, they will tell you exactly how to set it up. It's a very well-known thing. Another interesting tip for improving performance of your web servers is taking all of your static data and putting it on some kind of a web storage layer, such as Amazon S3 or maybe a content delivery network such as Akamai. The benefit of that is for your static data, which doesn't change, which doesn't need to be updated all that often, if you put that data somewhere else, it's going to relieve your servers from having to do work. And that's always good, because somebody else doing the work for you cheaply is going to be much better. So I would say, as much as you can, put a lot of static data elsewhere, and that's going to drastically reduce your server load. So when we talk about servers, we could be talking about physical servers, or we could be talking about cloud servers. There are pros and cons to both of them, but basically it boils down to your capital expense versus your operational expense. Your cloud doesn't require capital outlay. You don't have to buy servers, but you're going to have to pay by the hour. When you buy servers, you have to pay up front, but your operational costs are going to be lower. Cloud does have one interesting benefit, which is it's trivially easy to add capacity. If you need more servers, just start them up. You don't have to wait. You don't have to process a purchase order, buy a big chunk of metal. And then what happens if your players leave, right? If your game doesn't work, you're stuck with a physical machine. But if you're on the cloud, you can just turn off instances and reduce your operational costs. One interesting part about the cloud is the neighbor effects, which is kind of unexpected. Basically, your VM, your virtual machine is not the only one running on a physical machine in a server, in a server farm, which means that if your neighbors, if the other virtual machines on that server are misbehaved, for example, they do burst network activity or something like that, that might have a knock-on effect on you. You might start noticing weird latency problems or stuff like that. It's not really avoidable, but just something to look out for. If you start seeing weird problems on just one of your many servers, it could have bad neighbors, essentially, and that's just something you have to work with. The three popular service models are sort of, one, you just rent virtual machines, you do everything yourself, install the operating system, run whatever software you want. It's most control you can have. Then you have a platform level, such as Microsoft Azure, Google Google App Servers, and so on, where you upload your code to work within their sandbox. And if you can make your code work within the sandbox, if you don't have legacy software to run and so on, it's a very appealing kind of a thing, because they will handle a lot of the scaling for you. They will handle running more running more virtual servers and then reducing them, either by providing an API or a web interface, or maybe automatically. And then the last layer is software as a service, which is a service like parse.com. They will provide leaderboards, for example, or cloud storage. They typically don't let you run your own software on their servers, maybe in a very limited way. People do use them, but maybe if you're running your own kind of game servers, probably not them. You're probably going to end up with either infrastructure or platform layers. So the trade-offs are, as we mentioned, you trade off more control and also more work on one hand, and on the other hand, easier, but maybe a little bit more expensive. How do you choose which one to use? I mean, if you have legacy software, then clearly you might have to run your own operating system. If you don't, it's kind of up to you. I would actually, and we'll come to that at the end, I would actually probably start with a managed service on the platform level. And my rule of thumb is basically trying to keep the costs below 10% of gross revenue and always keeping it on a per user basis. Because once you get past 10% of gross revenue, then your server costs start, they start hurting. But below that, I mean, it's a rule of thumb, but it's kind of a useful one. And just keeping in mind that your OpEx, your operational expenses for servers should grow linearly with the number of players. If you notice your OpEx growing super linearly, then you're obviously going to have a problem. So let's talk about some example cloud solutions. And I'm going to use Amazon examples just because I'm most familiar with them, but Google and Microsoft have their own offerings in this space as well, which are worth researching. So we'll talk really quickly about web storage, web object storage. We'll talk about virtual machines, and we'll talk about databases from the perspective of kind of interesting gotchas and interesting problems. So Amazon S3 is the web object storage offered by Amazon. It's your typical sort of, you upload an object and then becomes available for download over HTTP a little bit later. Very sort of like straightforward stuff. It's great for static content, your big images, your sound files, your movies and animations, that kind of stuff, because it's really cheap and you don't have to pay for server cycles. There are a couple gotchas. People have tried using this for the player storage, for like, player inventory or whatever, and the problem is eventual consistency. So, they run this on their own server farm, and you upload, let's say you upload 100 files. And one player who lives nearby will get all those 100 files immediately. Another player who lives far away, they might initially get 50 of those files, but the other 50 will not be available yet. Another player who lives somewhere else might not get those files at all until a second or 2 seconds later. We're not talking a huge delay, but we're talking some number of seconds, maybe. Definitely some number of milliseconds. Basically, the delay might be unpredictable, and that's the bottom line. When you write your game code, it has to live with the possibility that the data it's requesting is going to be stale. And it won't know that the data is stale. It will just get some data. So that's one difficulty about this. And sort of transient failures. Sometimes you just might get 404s, and you have to deal with it. But if you can architect your game to live with that, then this kind of storage becomes really useful. In terms of virtual machines, Amazon's offering is called Electric Compute Cloud. Very useful, right? You start up a virtual machine, you install your operating system, and you do whatever you want with it, which is great. You can write your own software, whatever. The one interesting aspect of this is that a small number of instances at random points will just stop working. They will stop responding to the network. And it's a very low number. I've observed maybe, on a large server farm, maybe 1 to 5% per year will exhibit this. But the problem is that at that point, there's really no good way to deal with it other than just shutting them down and restarting them. And if it's your web server that's replaceable, that's no problem. If it's your database that goes down, then you have a problem, right? Because your game will stop working properly. So people do different things about that. You can, typically you would end up having multiple replicas, and then if one database goes down, you switch to a replica really quickly. The other thing that's kind of interesting about EC2 is that it has a distinction between the local hard drive on the VM and the network attached storage. And the local hard drive gets completely wiped when the instance shuts down. So that's a problem. Hopefully, if you have a database, if you have a database on that server, don't keep it on the local hard drive, keep it on network attached storage. Their offering is called EBS. It's basically like a network attached hard drive. You just write to it. You can attach it to a different machine. It kind of just works. It is more expensive, so that's one downside, but you have to use it for persistent data like databases if you're running your own database. And the downside, of course, is that I/O performance is going to be much lower than just your own hard drive because it has to get serialized over the network and all that stuff. But that said, it's useful. So this is also kind of why people are shying away from running their own databases and their own stuff on virtual machines, because there's a lot of these little gotchas that can get you. So the newer stuff that's showing up is platform as a service offerings. Again, Microsoft Azure, Google App Engine. They will do things like host the database for you and scale it automatically, adding more virtual servers as necessary. And even with web servers, you upload your code that works within their sandbox, and their service, either through a web API or automatically or through a web portal, lets you add capacity. It's very appealing, and if you can work within their pricing model, it's kind of interesting. Now, the thing to keep in mind is that it is probably going to be more expensive than just running your VM, but you're saving time. And you can also do a hybrid, right? You can do a database that's managed and your game code by just renting VMs and writing your own code. And the last thing I wanted to say is keep track of your servers as they're running. Set up monitoring. And if you're working with a vendor, they will probably have their own monitoring setup. Or you can install your own Nagios or Munin, or there's a bunch of network monitoring packages. Basically, what you want is a dashboard that shows you at a glance all of your servers and what they're doing. Your CPU load, your network load, and all that kind of stuff, I/O, so that you can tell, for example, if one of those servers is starting to spike, okay, compared to others are not spiking, okay, there's something wrong with the server, maybe I need to restart it. Or on the other hand, if you push new code to production and you see a huge spike across all of them, you know you've introduced a problem and maybe you need to roll it back. So that's sort of very quickly going through that. We're coming to the very end of the talk. You don't need to write down these URLs really quickly. I will make this talk available after this on Twitter. But there are some very good resources about this that you can read up on. Highscalability.com is kind of a standard go-to for web scalability solutions. They have a lot of material on there. And just to close it out, sort of looking forward, looking into the future, if I was starting a new multiplayer game at this point, I would probably look at using managed solutions quite a bit, but definitely make the code ready for scalability from day one, not just write some server code and think about scalability later, but worry about how am I going to support n number of players where n could potentially be big. It doesn't take that much work when you start out like that, but it takes a lot of work to reverse engineer your code to work with it. I would probably use a managed database for persistent data. I would probably host my own in-memory database for transient data like user stats, that kind of stuff that's not important, and probably self-hosted my own web servers in a high-performance language so I can control the most of it, but that's that's a personal perspective kind of a thing. So yes, that's that, and thank you very much for being here this early. And I will take any questions. You can either ask now or after the talk. Thank you.